I thank all of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of December 2023. The given question is from the section Real Analysis and it is related to the divergent sequences. It is related to the divergent sequences. This question is placed in part C, which is a multiple select question. There can be more than one answer and the question carries 4.75 marks and the question ID is 704062. This question is suitable for all these examinations. Right. The given question is, let x be a real number. Which of the following statements are true? We are given four options. Option 1. There exists an integer n greater than or equal to 1 such that n square sine 1 by n greater than or equal to x. Option 2. There exists an integer n greater than or equal to 1 such that n cos 1 by n greater than or equal to x. Option 3. There exists an integer n greater than or equal to 1 such that n e power minus n greater than or equal to x. Option 4. There exists an integer n greater than or equal to 2 such that n log n to the power of minus 1 greater than or equal to x. Right. Let's now discuss the solution of the problem in detail. We recall the definition of a divergent sequence diverging to plus infinity. Let an be a given sequence of real numbers. The sequence an is divergent and diverges to plus infinity, that is, limit n tends to infinity of an is infinity if and only if for each m greater than 0 there exists an integer capital N belongs to the set of natural numbers such that an is greater than m for all n greater than or equal to n. So we say that the sequence an is divergent and diverging to plus infinity, that is, limit n tends to infinity of an is equal to infinity if and only if for each m greater than 0 there exists an integer n belongs to n such that an greater than m for all n greater than or equal to capital N. So, in the light of this definition, it is sufficient to prove limit n tends to infinity of an is infinity. Right. We discuss the options one after the other. Option 1. There exists an integer n greater than or equal to 1 such that n squared sine 1 by n greater than or equal to x. Right. So consider the sequence an where an is equal to n square sine 1 by n belongs to n set of natural numbers. Note down that every term an is positive for all n. Right. Now, we compute limit n tends to infinity of an, that is equal to limit n tends to infinity of n square sine 1 by n, that's equal to limit n tends to infinity of n multiplied by sine 1 by n by 1 by n. This n square is written as n by 1 by n. Right. So the limit of the product is equal to product of their limits. Limit n tends to infinity of n multiplied by limit n tends to infinity of sine 1 by n by 1 by n. And as n tends to infinity, 1 by n tends to 0. It amounts to, say, limit x tends to 0 of sine x by x. That is 1. So that is equal to limit n tends to infinity of n, which is obviously infinity. So when it is infinity, by the definition, there exists an integer n belongs to a set of natural numbers such that an is bigger than x. The x is the given real number for all n greater than or equal to capital N. So the option 1 is true. Now one may ask a question. So an is sine n square into sine 1 by n. Sir, where is this less than or equal to? It is greater than or equal to. Where is this equality? So equality doesn't arise in this case, and x is a positive real number because x must be a positive real number because all the terms are positive. So thus the option 1 is true. We go to option 2. Option 2, there exists an integer n greater than or equal to 1 such that n cos 1 by n greater than or equal to x. Consider the sequence an where an is n times cos 1 by n. N belongs to a set of natural numbers. Note down each of the terms. Every term is positive for all n. Limit n tends to infinity of an is limit n tends to infinity of an is n cos 1 by n. And that is limit n tends to infinity of n multiplied by limit n tends to infinity of cos 1 by n. As n tends to infinity, cos 1 by n is 1, cos 0 is 1. So that will be limit n tends to infinity of n, that is infinity. Therefore, there exists a positive integer. There exists capital N belongs to n such that an is greater than x for all n greater than or equal to, and thus option 2 is true. We move on to the option 4. Option 4. There exists an integer n greater than or equal to 2 such that n multiplied by log n to the power of minus 1 is greater than or equal to x. Consider the sequence an where an is n multiplied by log n to the power of minus 1 where n greater than or equal to 2 and each an is positive. And why n is greater than or equal to 2? If you take n is equal to 1 and there is a log 1 is 0 to the power of minus 1, it's not defined. So therefore, this n will start from 2 onwards. Agreed. Limit n tends to infinity of an is limit n tends to infinity of n log n to the power of minus 1, that is equal to limit n tends to infinity of n by log n, and which takes the infinity by infinity form. We use an indeterminate form. We use L'Hopital's rule. So differentiate numerator and the differentiate denominator and then apply limit. Limit n tends to infinity of 1 by log n, derivative is 1 by n. That is limit n tends to infinity of n, that is infinity. Therefore, there exists a positive integer n such that an is bigger than x for all n greater than or equal to n greater than or equal to capital N. Therefore, option 4 is also true. So that's 1, 2, 4 are true. Let's look at option 3. Option 3. There exists an integer n greater than or equal to 1 such that n e power minus n greater than or equal to x, consider the sequence an where an is n e power minus n. N belongs to the set of natural numbers and each an is positive. Limit n tends to infinity of an is limit n tends to infinity of n e power minus n. That is limit n tends to infinity of n by e power n, which takes the infinity by infinity form, which is an indeterminate form. We use L'Hopital's rule to evaluate it. So differentiate numerator and differentiate denominator, then apply limit. Limit n tends to infinity of 1 by e power n, that is 0. So what's happening? It is not diverging. It's not diverging. It is not diverging to plus infinity. It is converging to 0. Converging to 0. Therefore, there does not exist a natural number, capital N, such that an is bigger than x. So, option 3 is not true. Therefore, the answer to this question is options 1, 2 and 4. That is the detailed discussion of the solution of the given question from the real analysis, which is based on the definition of the divergent sequences diverging to infinity. And this is definitely a very easy question. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.